Okay, hey Daniel. We just went through example 3 and I didn't record, so I'm going to start on example 4 and then I might bump back to example 3 here in a bit. So example 4 and example 5, we're going to do those and we'll figure out those and then we'll come back. All right, example 4, we have another picture and a rocket is being launched and then we have a camera that is watching this rocket being launched. But what shape is this? A right triangle again. So I'm going to guess that the equation is probably going to be the Pythagorean theorem again, right? I don't know. Let's see. So I separated out into what equation are we going to use? What do we know? What are we trying to find? Like if you are stuck and you don't know what to do first, that's what I do first. I separate out all the things, all right? So equation, I'm going to put a squared plus b squared equals c squared because I think that's what we're going to do. Okay? There's nothing else that can go on here. All right. This figure shows a camera that is mounted on a point that is 3,000 feet from the launching pad. Is that 3,000 feet going to change? No. Like this camera will stay here. The launching pad will stay there. This is not going to change. Okay? So keep that in mind. If the rocket is rising vertically at 880 feet per second. 880 feet per second. Okay? First of all, let's name our sides. If we go on this a squared, b squared, c squared, what side is side A? Do you want? The bottom one, side A. Okay, what's side B? This side one, and then C has to be here, right? Right, okay. So if this is 880 feet per second, that's how much that is changing. So B isn't 880. What is 880? The rate at which B changes, which is called what? dB dt. The rate at which B changes with respect to time is 880 feet per second. Does that make sense? That's the rate. This is just the length of B. I don't know how many seconds we've been going, right? If we've been going for 2 seconds, that's going to be like 1760 or whatever, right? Okay, so that's going to determine how long that is. But the rate at which it's changing is 880. So dB dt. That's something I know. dB dt is 880. Cool. If the rocket is rising vertically at 880 when it is 4,000 feet above the launching pad. So what does that tell us? When it is 4,000 feet above the launching pad.
That's how high it is.
That's how high it is, right here. So what is 4,000? The 4,000 is B. Yeah, B is 4,000. Okay? Which I could figure out, that means it's been rising for like almost 5 seconds, maybe like 4.5 seconds, right? So B is 4,000. All right, that's what I have. How fast must the camera elevation angle change at the instant to keep the camera aimed at the rocket? How fast must the camera elevation angle change Okay.
We gotta do like cosine stuff, don't we?
Yeah, this is not an a squared, b squared, c squared thing.
No, don't say it.
This is not an a squared, b squared, c squared thing.
Don't say it.
Okay, we don't care about c. We're talking about the way that this angle changes. Let's give that angle a name. Yeah, I like it. Theta. Let's call it theta. Okay? So, if we're trying to figure out the rate of change of this angle, what's that called? What's the rate at which that angle change is called? That angle is named theta. What is the rate I'm just trying to figure out what variable it's called. What are we going to call the variable that's the rate that this thing changes?
Oh, the whatever d theta.
We're trying to find d theta dt, right? The rate at which that angle changes. Boo. Okay, all right, so we're trying to find d theta dt. Okay, we are not doing a squared, b squared, c squared. Boo. Dang it. Okay, what are we doing? SOHCAHTOA, which one is it though? Is it which one is it? SOHCAHTOA. Yeah, it's gonna be tangent. Okay, so tangent. Let's go this. Okay, my equation is going to be tangent of what?
Theta.
Theta equals
Opposite over adjacent.
opposite over adjacent. What's the opposite side?
dB dt.
No.
880.
What do we name the opposite side? We named it B, right? Over the adjacent side, which we named
3000.
A, right? Okay, we'll get to that. Hold on. Okay. All right. We know that. Here's the deal. We know, because I want to there's some things that I need to plug into this equation, but there's some things that I have to wait to plug in until after I take the derivative, right? So theta, is theta going to change as this rocket rises? Yes, it's going to get bigger, right? Okay, so that means I have to wait on him. Anything that's going to change, I have to wait until after I take the derivative of to plug stuff in. All right, B, will B change as this rocket rises? Yeah, so I have to wait on him. A, will A change as the rocket rises? No. So I get to plug in 3,000 in for A. Yeah? Okay, that makes my life a little bit easier. Okay, we have to take the derivative of this first, but let's do some options. Do you want to multiply the 3,000 over to the other side
Yeah.
to make it so we don't have a fraction? Sure, let's do it. Okay, so we have 3,000 tangent theta equals B. Okay, now we just have to go through and do the derivatives, right? I'm going to start with the right side because that's your derivative. What's the derivative of B?
dB dt.
1 dB dt, right? 1 dB dt. Okay? All right, so there is that. And I have to find the derivative of 3,000 tangent. The 3,000 is not doing anything. I don't have to do the product rule, true? Like if this is F and this is G, I can if I want to, but 3,000, his derivative is going to be 0, right? So I don't have to do the product rule. I could just like let the 3,000 chill on the tangent. Do you know what the derivative of tangent is? I think it's like secant squared.
Secant squared x.
Secant squared theta. Okay. So this will be 3,000 secant squared theta times
D theta.
d theta dt, right? The derivative of the inside is d theta dt. Okay. Woo! That's my derivative. Okay.
Yep.
All right. Beautiful. We don't even have to plug b in anywhere. Right?
Nonsense.
Interesting, interesting, interesting. Okay. All right. Let's plug in things that we know. Oh, we do need B though. Okay, so we have 3,000 secant squared of theta. Do we know what theta is? No. How do I find theta?
Well, you do what we were gonna do.
Yeah, I know that at the moment I'm trying to find this, B is 4,000 and A is 3,000. Can I use that to find theta using tangent? I know that tangent of theta is equal to opposite over adjacent, so 4,000 over 3,000. Now I could cut those zeros out and say tangent of theta is 4/3.
53.1.
53.1 degrees. Cool. You did inverse tangent, right? Okay. So 53.1 degrees is going to go there times d theta dt. What's d theta dt?
What was it? Like 80? No.
D theta dt is what we're solving for, right?
Oh. So
Yeah.
just leave it.
Yeah, so we should leave d theta dt. I want to know the rate at which the angle is changing, right? And then 1 dB dt, and dB dt is changing at a rate of 880. So 880. Okay. Gross. Do you know how to do secant on your calculator?
You told us, but I forgot.
You don't have a secant button on your calculator. But what do you have?
Is it like
A math button.
it's like something? It's
You have
like-
cosine, and cosine is the opposite of secant, right? So secant squared of 53 would be the same thing as 1 over cosine squared of 53. So what you're going to do is you're going to go cosine of 53.1. You're going to square that, and you're going to take 1 divided by that number. And you have to take it times 3,000. Did you square the cosine of 53.1?
Yeah.
What'd you get? What'd you get? Did you take them times 3,000? I'm trying to decide if I want to move this over to the other side first.
Do
Do you want to move him?
I put all of that on the bottom
What?
of 880.
You don't want the 3,000 on the bottom.
Okay.
Okay. So here's the deal. Ready? Let's do this instead. Let's solve for d theta dt. So we have all this stuff plopped in, right? Okay. If I'm trying to solve for d theta dt, I'm going to divide the 3,000 over, right? What does that make? What's 880 divided by 3,000? Now, if I'm trying to divide the 1 over cosine squared over, I'm just going to multiply by cosine of 53.1 squared. Okay, so take the 0.293 and multiply by cosine of 53.1, that whole thing squared, times the 0.293. And d theta dt is something. It should be a kind of a small number-ish. We should talk about the rate that the angle is changing. Cosine of 53.1 squared times 0.293. I got 0.1056. 6. You probably used the full decimal of 0.293 though, didn't you? So should it be a 7?
Well, that's what. Yeah. Also, when I just did it like this.
Yeah, that's fine. Is that what you got though? Was it
Yeah.
0.1057? Okay, what does that mean? The rate that the angle is changing is that much what? Yeah. Degrees per second, right? Because your angle is in degrees, right? So it's changing that many degrees per second. Yeah. Yeah. That's not a lot. Why is that not a lot?
Doesn't it slow down the farther away you get?
The higher up in the air
Yeah.
it gets, the more it will slow down.
Yeah.
Yeah, because it'll be like above you, right? So you won't even have to like change the angle. But why is that so small? Like that's like it has to like 10 seconds have to go by before I've changed 1 degree. Why?
Because it's 3,000.
Because we're a mile away from the thing, right? It's gonna be a while before I have to change and arc my camera up, right? Does that make sense? We're a mile away from this thing. It's not like I'm right underneath of it where I'm gonna have to shoot my camera up real fast, right? So that does make sense. Oofda, that was icky, right? Ugh. All right, let's see what this one does. Let's see if this one's a little easier. I don't know for sure. We're draining water through a conical filter. Okay, so we got a cone going on, and I'm going to imagine that we're doing volume of a cone, right? Do you know what volume of a cone is?
Absolutely not.
Do you know what volume of a cylinder is? Here you go. Here's what volume of a cone is. Volume of a cylinder, right? Volume is the area of the base times the height, right? So if this is height and the area of the base is a circle, right? Pi r squared is the area of the circle times the height is a third of it, right? So this is the volume of a cylinder, right? Pi r squared h, that's volume of a cylinder, okay? Volume of a cone is 1/3 of that, pi r squared h. Yeah? Yeah. I can't believe that you know the volume of a sphere and not the volume of a cylinder.
Why would I know the volume?
You knew the volume of a sphere yesterday off the top of your head. It just amazed me. I don't know. Anyway, whatever. Okay, all right, here we go. So that's probably the equation that we're doing because we're doing volume and it's like draining out, okay? Now, let's keep in mind, this one is draining, right? The rocket was shooting up, so it's increasing in distance. This one is draining, so it is decreasing in distance. So the height, like dh dt or dy dt, might be negative, right? Because it's draining out. Okay, so just FYI. All right. Suppose that liquid is to be cleared of sediment by allowing it to drain through a conical filter that is 16 centimeters high and has a radius of 4. Okay, so they are giving us those values, and they call, for some reason, they call the height y. Do you want to call it y, or do you want to call it h? I want to call it h, because that's what my formula is in. Can I switch that y to an h?
I don't see why not.
Sure. Okay, let's do it. So they are giving me the information. They're saying we're focused on specifically when the height is 16 and the radius is 4. Okay. But I don't know what dHdt is, and I don't know what drdt is. So we're going to figure that out. Suppose also that the liquid is forced out of the cone at a rate of 2 cubic centimeters per minute. So what's that the rate of? The liquid is pouring out at 2 cubic centimeters per minute. So that's d what dt? Yeah, dv dt is changing. Right? dv dt is changing at 2, but it should be negative 2 because it's forcing out, right? So they're not giving us dH dt and dr dt, which is what I thought they were going to, and have us solve for dv dt. They're giving us dv dt and probably having us solve for dH and dr. Got it? Confusion? This is a lot. Okay. Do you think that the depth of the liquid, which I'm going to guess is the height of the liquid, will decrease at a constant rate?
No.
No, because what have we decided? As the thing forces out, it looks like it starts to like go real fast, right? Out the thing. So dH dt will increase as it moves, as the water moves further and further out, right? So the speed of the height changing will increase, right? dHdt will increase as it moves down. Does that make any sense at all? Clear as mud. Sure. Okay. Find a formula that expresses the rate at which the depth of the liquid is changing in terms of the depth, and use that formula to determine whether your conclusion is correct. Okay, we know that that's the answer, so I'm going to skip part B. Okay, at which rate is the depth of the liquid changing at the instance when the liquid of the cone is 8 centimeters deep? What are you talking about? Now we're changing it to 8 instead of 16? I don't want to do that. So 16 is at the top. Boo. Oh, it's fine. We could just change the H to that. Okay. All right. Okay. All right. At what rate is the depth of the liquid changing at the instant when the liquid in the cone? Okay, so at what rate is the depth of the liquid changing? So at what rate is depth changing? What are we solving for? Height, right? We're solving for dH dt. dH dt, yeah. At what rate the depth is changing, dH dt. Okay, so as far as it goes with our equation, we've got it. Volume equals 1/3 pi r squared h. Okay, we're trying to find dH dt. Got it. And what do we know? We know that dv dt is -2. But h and r are no longer h and r. H and r are, they're changing it. H was 16 when it was full, and r was 4 when it was full. Right? But now they're saying h is 8. Okay, so now it's here. Right, so we're half of the 16. So what's the radius? 2. Is the radius 2? Those are directly related, right? They're the same proportion. True? Right? The smaller cone is proportionate to the bigger cone. So if we're now half, the other one's going to be 2, right? They're proportionate, right? Like 4 over 16 equals r over 8, right? Cross multiply and divide, and that should be 2, or that should just make sense. The radius is going to be 2, so that's something else that I know. Okay. We're going to end up with one dead end here. What time do we get out here? Oh, we got a while. We're gonna end up with one at a dead end here in just a second. But let's do this first. Let's do the derivative of the equation. Let's see where our dead end leaves. Okay, derivative of v. dv dt. 1 dv dt, or just dv dt. Okay, equals. What do we have to do? Product rule, because we have two variables, right? So I'm going to say that this is the f, and this is the g. Okay? We have f prime g plus g prime f. Okay. F prime g plus g prime f. Okay. All right. If that whole thing is f, what's f prime going to be? Drop the 2 down. 2/3 pi r dr dt, right?
Yeah.
Okay. Times g, which is just h. Perfect. Okay. G prime, what's the derivative of h? dh dt. And then f is just that whole thing. 1/3 pi r squared. This is slightly unpleasant, but we'll make do. It'll be fine. Okay. What are we trying to solve for? We're trying to find dh dt, which is right here. Okay. So plus, that guy's going to stay dh dt. Cool. All right, times. I know this is 1/3. This is pi. What's r? We say it was 2. Okay. All right, so I've got that all plugged in. I know that dv dt is -2, right? So I've got 2/3 pi. R was 2. dr dt. What's dr dt? Oofda.
Wait, what's R?
We don't know what dr dt is.
Oh, the rate that the radius changes.
Okay, is the rate of the radius changing going to be constant? No, it's going to start to slow down, right? Okay, so we don't know what that is. So this is a question mark. That's the dead end that we're going to run into. Not a dead end. Detour, because we got to do something else. H is how much?
8.
8. Okay. We have to figure out what the heck is dr dt. Okay, here's how you navigate this dead end. Ready? You know, like last time we had a dead end and we were like, oh, we had to plug that into the Pythagorean theorem in order to figure out what C is, right? And like do that thing, okay? Okay, what is the relationship between H and R? What's the relationship between H and R? When the height was 16, the radius was 4. When the height was 8, the radius is 2. H is equal to 4r, right? 4 times the radius gives you the height. Okay? All right? This is the missing piece. Are you ready for this? We don't know. Are you ready? We don't know what? What don't we know? No, we don't know dr dt, right? Here's what we're going to do. We know that h is equal to 4 times r, right? Let's take the derivative of this little guy. What's the derivative of h? dh dt. What's the derivative of 4r? 4 dr dt, right? Okay? We don't know what dr dt is, right? But we do know dh dt is how much? Is dh dt 8? We don't know dh dt either. We're solving for dh
That's
dt.
what I said. You're like,
Nah.
Holy air.
Okay.
I don't know what
Okay.
DRDT
We can do this, though. We can do this. It's fine.
Ow.
Okay? dr dt is equal to dh dt divided by 4. True? Okay, so in place of dr dt, we're going to do dh dt divided by 4.
I love it when we do that.
Fractions on.
Okay? Because now we only have one variable going on instead of 2 variables. Okay, let's simplify some stuff. I love it. Okay. All right, let's multiply some junk. I am dividing by 4, right? But then I'm taking times 8. So that is 2. But then I have another 2, which is 4 times 2/3.
8 thirds.
8/3.
8 thirds.
This is 8/3 pi times dh dt. True?
I'd say so.
Plus. 2 squared is 4. 4 times a third is 4/3 pi dHdt. Yes? Okay, it's looking better. Now what can we do? You can, or can I add these two together?
Yeah.
What's 8/3 pi plus 4/3 pi? You know this.
4 pi.
Yeah, 12/3 pi, which is 4 pi. 4 pi dHdt. Gross. And then what?
Divide over.
Divide over. I'm dividing 4 pi over. And that reduces to negative 1 over pi is what dHdt is. What's 1 divided by pi, by the way?
Like
Negative 0.159? Okay. What per what?
that happens to be the rate at which the
Height is changing, which with respect to time. And the height is in centimeters per second? Blah, 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 blah. Minute. Centimeters per minute. So it is decreasing at a rate of that many centimeters per minute. Now, it will speed up, though, because the height is changing, and it's going to start to speed up, and as it goes out, right? So it might reach like negative 0.3 centimeters per minute as it gets like all the way down near the bottom. But that is that. That was like the big jump in the middle, right? We did not know dRdt. That was a problem, but we did know that we can relate dRdt and dHdt and then solve. What a big darn mess.
Okay, why did the snowman call his dog Frost?
Woo! Okay. All right.
What'd you say?
I was
Why
going
did the snowman call
to.
his dog Frost?
Yeah. I am. Daniel, I'm going to go through this one with you.
Frost bites.
I'm going to go through this one with you. So I'm going to erase what we have, and then I'll go through and then we'll see if this makes sense. Okay. So you boys, start looking at homework problems. You have like 7 minutes. I'm gonna go through this one with you.
Real quick and get my t-shirt, my Billy t-shirt.
What are you talking about? For
I'll
what?
go to my pickup.
I don't care. I'm gonna go through this problem with
I really did.
I'm
With,
not gonna lie, bro, my chair, this stuff's stupid.
It's a lot. It's a lot. Okay. Equation.
Probably one of the most difficult.
What do we know? What are we trying to find? Okay. Example 3. We have a baseball diamond, and they say that each side of the baseball diamond is 90 feet, or like the distance from each plate is 90 feet. 90 feet, 90 feet, 90 feet. Okay. And then they have a person running from second place to third base. Okay. We do not know how far they are, or like how that is going. So let's call that guy X. And then the boys said, okay, this is our right triangle right here. So let's call this guy C if we want to, right? I guess instead of using X, we could call that A. Let's call it A instead. A and C, right? And then this would be like your B value. Okay, so A, B, and C. And this is a right triangle. So the equation that we guessed was the Pythagorean theorem. A squared plus B squared equals C squared. Now, we guessed that for this example down here, and then we ended up being wrong. But it is, in fact, A squared plus B squared equals C squared. We're looking at the sides of that right triangle. Okay. Sides of a baseball diamond are 90 feet. Suppose that a player is running from second base to third base at a speed of 30 feet per second. Okay, so what's happening is this rate of change is 30 feet per second. So the rate at which this variable is changing is 30 feet per second. And the rate at which A is changing is another name for dA dt, right? The rate at which A, which is this distance, is changing is 30 feet per second. Okay? So I'm going to say dA dt is 30. That's one thing that we know. dA over dt is equal to 30. We know that, okay? At the instant when he is 20 feet from third base, okay? So if he is right here and that is 20 feet from third base, that means A is 20. Okay, so I'm going to put that in another thing that we know. A is 20. Okay. And and then it says at what rate. So we're trying to find d something dt is the distance from home plate changing. Okay, so this is my distance from home plate, and if I'm trying to denote that as a rate, this distance is called c, and the rate at which c changes is dc dt. And so I'm going to try to find dc dt. And that is that. Okay. Sorry, I'm talking to myself, but I'm recording something for another student. So just don't mind me. I'm just the crazy lady talking to herself. Okay. So what we have going on here is we have this equation, a squared plus b squared equals c squared. Now, some things I am allowed to plug into that equation before I take the derivative, and some things I have to wait until after. For instance, if I'm looking at this triangle, I can plug stuff into that triangle as long as it won't change. Okay, so as this person runs, if that side will change, then I can't plug it in until after I take the derivative, okay? So if we're looking at A is this side right here. A will change, right? A is changing from 20, but it's going to get smaller and smaller and smaller, okay? So I have to wait on the A has to stay A, okay? Same thing with C. C started going here, right? And then it got smaller and smaller and smaller, okay? And so C, we will have to wait for C because he will change. But this B value, no matter what, this side B is going to be 90 no matter what, okay? So B, we can plug 90 in for B and be good, okay? All right, now we have to find the derivative. So if we're finding the derivative of a squared, that is 2a dA dt, okay? If we're doing 90 squared is 8100, but if I'm taking the derivative of that, that's going to be 0. It's going to cross off. So I really don't even need that value there. And then the derivative of c squared is 2c dc dt. Okay, and now I'm just going to plug stuff in. So we are trying to solve for dc dt. I'm going to circle him, okay? I know that dA dt is 30, so 30 goes in here. And I know that a is 20, so 20 goes in here. So 2 times 20 times 30 equals 2 times c times dc dt, and dc dt is what we're solving for. But the problem here is I don't have in my no box, I don't have what c is, and I need a value to plug in for c. And so this is where we have to kind of do some searching. And if we know that at the instant that I'm interested, if we know that a is 20 and b is 90, I can figure out using the Pythagorean theorem what c is at that very moment and plug that in for c, okay? So a is 20, so 20 squared plus 90 squared equals c squared, okay? 20 squared is 400, 90 squared is 8100, and so this will be the square root of 8500 is what c is. And I don't remember what that was, 92.2 or something like that. A square root, 8500. And yeah, 92.2. Okay, so I'm going to plug 92.2 in for that value. And if we take that times 2 on this side, this is 184.4 is what that will be. Okay, if I'm trying to solve for dc dt, I'm going to divide this whole thing by 184.4. Okay, we said 2 times 20 times 30 was 1200 divided by 84.4. And that was 184.4, not 84.4. 1200 divided by 184.4 is 6.5. And that is what dc dt is. And dc dt is the rate at which c changes with respect to time. And c is in feet, and time is in, what are we in, seconds? Feet per second. So this c, which originally started off at second base, it is getting smaller and smaller as this person runs, right? And it is changing at a rate of 6.5 feet per second. Okay, so like this distance is getting, or this distance is getting smaller by 6.5 feet per second. Okay, now that probably won't stay the same because obviously this person's gonna have to slow down as they get toward third base, and they're speeding up as they leave second base. So the rate at which this is changing is not going to stay the same, but at this very second when these things are happening, dc dt is changing at 6.5 feet per second. Okay, so sometimes they will give you everything that you need. Sometimes you have to do some behind the scenes work like we did over here to solve for what c was. Kind of like over here we had to do some behind the scenes work to figure out dr dt. Ooh, awful. Okay, all right. I hope you're enjoying yourself at your brother's graduation, and we will see you, I don't know, in a couple days.